Welcome back to particle physics and a standard model. This is lecture 45, and in the last class we saw how one of the delta m squareds in nature was measured using atmospheric neutrinos. The idea was that cosmic rays that are around a g in energy hit the nuclei in the atmosphere, which produces a hadronic shower consisting mainly of pions, and the charged pions decay to muon and electron, muon and muon antineutrino, right, or depending on the charge it could be an anti-muon and muon neutrino. Now the muon or the anti-muon further undergoes weak decay to give an E, nu E and nu mu, right, and you can fix the fermion numbers correctly. So at the end of the day, from atmospheric production of neutrinos, you expect that the number of muon neutrinos you get should be twice the number of electron neutrinos, okay. But what people detected was that this ratio was around half to 1, and we saw that this happens because muon neutrinos are depleted on their way to the detectors through oscillations to other flavors, alright. So we can now turn this into an advantage and measure the delta m squared for at least this baseline. The baseline here being the typical chord length through the earth, through the interior of the earth, and that is about 1000 kilometers. And when you put that in, you find that for GeV neutrinos, the delta m squared that you can measure is around 10 power minus 4 electron volt squared. But actually using more sophisticated measurements, people have determined that the best fit is actually 2 times 10 power minus 3 electron volt squared. So it is not such a bad calculation, okay. And further we saw that we summarized the conditions for good measurements of neutrino oscillations, and of course we do not have any handle on the theta, which is given by nature, that is the mixing angle in the Lagrangian, in particular from the PMNS matrix actually, right. But the baseline is in your hands, you do not want to choose your baseline too small compared to the oscillation length, and indeed when we did the conversions right, we saw that 1000 kilometers was good for 10 power minus 3 electron volt squared of delta m squared, right. And finally we saw what happens in the fast oscillation regime. This is when the baseline that you get turns out to be much larger than the oscillation length, which is determined by the energy and the delta m squared, right. This situation can arise in astronomy, neutrino astronomy, when you have neutrinos from supernovae, extragalactic sources and so on. In that regime, all you can do is average out the oscillations and basically set the sign square in the probability to half, okay, a sign square that depends on the baseline, right. When you do that, the probability turns out to be half times sin square 2 theta, okay. And finally I said we will talk about the solar neutrino problem. We will see what the problem is and how that helps us measure many things, including the other delta m squared that we can measure in the neutrino sector, okay. So the problem, as I stated, was that neutrinos produced in the sun were only counted partially on earth, okay. So let us see how this happened, okay. First of all, what is the baseline we are thinking about? It is exactly 1 AU, right, astronomical unit. So how do you do the conversion now? First of all, what is this in centimeters? This is about 10 power 13 centimeters, okay. So you can check this, 1 AU is 8 light minutes, right. So that will give you 10 power 13 centimeters, And what does that correspond to? We already saw that 10 power 8 centimeters was 5 times 10 power 12 inverse electron volts, correct? So that would mean this is 5 times 10 power 17 inverse electron volts. Okay. Now, what is the energy of the neutrino here? So, let us quickly see how to get this energy. I am going to state a verifiable fact that the major channel of producing electron neutrinos in the sun is protons fusing, okay, to form deuterium, spitting out a positron and an electron neutrino. Okay. Is this a strong process, or is this a strong fusion or weak fusion? Of course, it is a weak fusion. Why? We have a neutrino, right? So, this is in fact the process that initiates the rest of fusion, fusion chain reaction. You need to start with this actually in the sun. Okay, you might wonder what is the use of having weak interactions in the universe. Well, that is what starts the entire fusion, the strong fusion chain reaction in main sequence stars like the sun. Okay, and that is what at the end of the day gives you sunlight, right? Okay, so that is the major channel. So, what does that give me? That means I can now compute roughly the electron neutrinos energy from just subtracting the masses of the deuterium and the positron from the initial state mass, which is twice the mass of the proton. Agreed? Right. So, I just have this. I am going to assume that the deuterium and the positron are roughly at rest for the energies that we are considering here. So, it is just a rough estimate, okay, but a pretty good estimate, and that turns out to be 2 times 938.3. This is all in MeV, minus 1875 minus 0.5. MeV, you can easily check this is about an MeV, about 1 MeV. Okay. Then I am going to go back here and ask whether I am going to get the correct delta m squared. Okay. So, now the delta m squared is again E nu over the oscillation length, which is what, MeV over 5 times 10 power 17 inverse electron volt. What is that? This is 10 power 6, let us just call this 10 power 18. Right. So, not minus 2 EV squared. I just written MeV as 10 power 6 EV, and 5 I am taking as 10 roughly, right. It is just an order of magnitude estimate. So, I have this, that is 10 power minus 12 EV squared, and this is absolutely wrong. Okay. Why? Because what we do measure, I just wrote it down, right. The measured value is from solar neutrinos 8 times 10 power minus 5 electron volt square, which is around 10 power minus 4, right? So we are 8 orders of magnitude off here. Okay. So what's going on here? Okay. So this is also tied to the solar neutrino problem. When you expect the using other measurements of delta m squared from not the solar neutrinos, when you put that into the oscillation probability, you expect a certain number of neutrinos, but then you get a far smaller number of neutrinos at your detectors. Okay. So what makes these neutrinos disappear in addition to the oscillations that we have been studying? That is the question. Okay. So I'm going to phrase this differently. This is what you get from vacuum oscillations. What do I mean? I mean that all the neutrino propagation that we have been looking at, we have implicitly assumed that everything is happening in vacuum, not in some medium, correct? In the Earth's case, we probably saw the neutrinos are propagating in some rock. So we should have put in some matter effects already, which I mentioned here, right? But otherwise, everywhere else we have been assuming implicitly that neutrinos are just propagating in vacuum, that is it. No air, no rock, no nothing, right? So the formula for the oscillation would change if the neutrinos are actually propagating in a medium. So that is not surprising, right? Because think of the propagation of light, right? Definitely light, the properties of light, the things that you can measure about light are different in vacuum and some medium, right? So it is not surprising that some medium effects or matter effects would affect neutrino oscillations as well. Okay. Said differently, at the end of the day, it is the Hamiltonian, right, that dictates the wave function evolution, right? And this Hamiltonian will be different in the vacuum and will be different in the medium basically. Okay. So I am going to say the Hamiltonian is modified in the presence of some medium, okay, and that medium in this case relevant to us would be a non-relativistic electron background. Okay. Remember that the sun, right, so that is the sun, contains what? It contains electrons all over the place, right. So even you are making neutrinos through this process, right, the PP going to D positron electron neutrino. So that neutrino is propagating through this electron background first, then it gets out and propagates in the vacuum, okay, and then it gets to earth of course. So here we are where we detect it, okay. So you should treat the propagation over here differently from there. That Hamiltonian changes literally when you get outside the sun, get inside the sun or outside the sun, okay. So with that in mind, let us see how now to write this modified Hamiltonian, okay. that comes from considering the Lagrangian for neutrinos interacting with electrons. Okay. So, first let me write the kinetic term because that is important for propagation, of course, right. So, that is the kinetic term, and I am going to rewrite the interaction with electrons this way. Okay. So, how does an interaction happen? Let me draw a Feynman diagram to illustrate that. So, I have this, right, a neutrino, okay, as written a positron, it could be have an electron also if I had drawn it differently through the W boson, correct. So, I have a diagram like this, right, but I also have diagrams like this, right, E plus E minus through a Z boson. Neutrino talks to a Z boson also. Right. So, all these vertices are weak vertices, and if the W and the Z bosons are heavy enough, I can, so to speak, integrate them out and put them into one coupling constant. What is the coupling constant? That is the Fermi constant, right, and it is literally 1 over V square. Okay. That of course is proportional to 1 over mw squared, that is what I have written here, the propagator, or 1 over mz square and so on. Okay. So, I am going to write this in this effective Lagrangian way, that is I have just basically integrated over this propagator, and you know, to me it looks like I just have a vertex that is like this, okay, neutrino like this. So, that vertex I am going to write as a Hamiltonian, sorry, as a Lagrangian term, that is this. It is a vector-vector interaction as expected, because we have been using vector bosons here, right. So, that is what it is in the Lagrangian. Okay. Now, if I went to the non-relativistic limit, then I have to consider what happens to this operator, right. I want to consider what is the expectation value of that operator now in the non-relativistic limit. Okay. So, what is that? Again, you might check this in the introductory chapters of any quantum field theory book. You will see that in the non-relativistic limit, this is nothing but the number density of the electrons. Okay, this is literally a counting operator that gives you the number density. Okay, and the mu is a Lorentz index. I have done nothing about that. That mu will be forced to be 0 actually. It is just a delta function. Sorry, not delta function, the delta tensor. Okay. Okay. So, and it turns out there is a factor of 2 also. Okay, where Ne is the average electron number density. Okay. Now, this I can put into my Hamiltonian. I can convert the Lagrangian to a Hamiltonian. I am not going to go through the steps, that should be trivial, right, but that can now be of course put into a Hamiltonian, and you will see that because it is in the Hamiltonian, the electron neutrino energy is now not just this, not just the momentum, of course this is at relativistic speeds, right, but also a factor of the number density of electrons that comes from this term. Okay, when you put it back into the Hamiltonian, you will see that is what this is, and you will find that similarly the energy of an anti-electron neutrino is that minus square root of GFNE. Okay, that is how it physically manifests itself, and this part, right, this GFNE, that bit is called, with the square root of 2, it is called the matter potential. So, it comes from the medium, right, the matter through which the neutrino is propagating. So, I would call it this is what technically it is a Fermi pseudo potential. It is not really a potential, that is why it is a pseudo potential, and it is technically called Fermi pseudo potential. Okay. So, basically this is like a refractive index. Okay, some people would argue this really is a refractive index. Okay, why? Because you have changed the dispersion relations, right, which is literally what, the relation between energy and momentum, that is literally what we changed up here, right. So, just like photons in matter, light through glass for instance, or water, right. And let me say one more thing for you to visualize what is going on. This is a result of neutrino, the plane wave. Now you have to think of neutrinos as plane waves, okay, as they propagate, right, as I have drawn here. The result of neutrino plane waves scattering in the forward direction. So, for people who know about the optical theorem and dispersion relations, this will be familiar, but if not, you can go look up, when you have plane waves scattering in the forward direction, that is exactly when you create a Fermi pseudo potential. Okay, and that is another way to express it is in terms of dispersion relations and refractive index. Okay, all the intuition from light propagation applies here. Okay, and this now would modify the propagation probabilities, sorry, the oscillation probability. Why? Because now the entire evolution, right, see this is the evolution, right. Regularly what would I have done? I start with this, correct, and then in general the Hamiltonian would have been like this. Okay, so you might wonder why is there a sine square just theta here. So we started with just cos theta sin theta. Why do we have all this? Why do you have cos square sin square theta? Because this is not the mixing matrix. Okay, these are not the mixing, literally this is not the mixing matrix. We are not just writing the mixing angles. We are going back and writing the Hamiltonian in terms of the flavor eigenstates now. That is why it has this weird structure. If it was the mass eigenstates, I would just have had this. Okay, in fact, not even m squared. I would have had just this in the mass eigenstate, but I am going back and writing the Hamiltonian in the flavor eigenstate, okay, in the flavor basis rather, and that gives me this. So, I am undiagonalizing the mass eigenstate. Okay, undiagonalizing the mass matrix, and I get this in the flavor basis. The reason I write it this way is that I have a modification now, okay, that will apply only to the electron neutrino, and that is this modification, right. That applies only to the electron neutrino, nowhere else, not in the off diagonal terms and not in the muon term either. So, I am going to write that modification as 2GFNE in the Hamiltonian. Of course, this is a 0, this is a 0, this is a 0. Okay. That is the modification we should put in to account for matter effects. Okay. Now, this can be solved, this Schrodinger equation now can of course be solved. We are not going to do that, but this is just to show you what is the physics behind matter effects. Okay. So, I am just going to state that solve now to get correct number of solar neutrinos. Okay. This is how people solve the solar neutrino problem, by invoking the matter potential in the sun. Okay. This is this whole thing is called the MSW effect, and you can read more about this in any standard particle physics textbook, okay, or take an astroparticle textbook, even better. Okay, there is a very interesting history in all this. So, this turned out to be important not only in solving the solar neutrino problem, but also fitting the delta M12 squared, okay, better to just call it delta M solar squared, and that is what we got as 8 times 10 to the power minus 5 electron volt squared, correct. There we are. Okay. Okay, so with this in mind, right, we should now talk about the ordering of masses. What do we mean by this 1, 2 and 1, 3 and all that? Okay, whatever delta M square you measure is what it is, right. We do not know what eigenstate we are really measuring here, correct. It is any two mass eigenstates, you take the difference of the squares that will correspond to some baseline and you just measure it, right. So, in the last few minutes of this lecture, I am going to actually talk about this mass ordering and introduce to you to the convention that is used to think about this mass ordering, okay. So, mass ordering. See, in the probability, right, we had this term, right, all these conversion probabilities from alpha to beta, right, were proportional to this particular term, correct, sine square of an argument that contains a delta M squared, right. So, since this is the term that is observable, right, that implies both delta M squared that are greater than 0, right, and delta M squared that is smaller than 0, right, are both possible, right. Why? Because it is a sine square, correct. That is the reason why. If it had been just a sine, you would know what the what the sign of the probability is. Of course, the probability is always positive. That is exactly why it came as a sine square. Since it is a square, there is a delta M square going to minus delta M square symmetry here, correct. So, you do not know whether you are measuring, in other words, right? Let's take 2 and 1, okay. You don't know whether you are measuring m2 square minus m1 squared or m1 squared minus m2 squared, right? Either possibility is there, okay. So, because of this ambiguity, you follow a certain convention to separate out the scenarios, okay. So, that convention will give us the different orderings that people think about for neutrino masses. So, I will take up this ordering in the beginning of the next lecture and leave you with just this fact that there is a convention that you can choose to neatly separate out the various possibilities. Okay, thank you. See you in the next lecture.